All right, here we go. Well, I'm not going to miss her, that's for sure. So, anywho, okay, we ended with this, talking about this yesterday. We were launching things vertically yesterday, and then we were showing the path and things of that nature. But now, today, we're going to launch things at an angle. Okay? So we're going to be able to throw something, okay, at an angle, and it's going to be launched at a certain height, so we got to factor that in. When we launch it, we have to factor in how fast we're launching it. We have to factor in the angle that we're launching it, because if I launch it at a much steeper angle, it's not going to go as far, because all the stuff's going to go vertically. Okay? So factor all that stuff in. And so yesterday, we ended class by saying that we have these formulas for an object launched at an initial angle of theta degrees with an initial velocity and an initial height. So the x part of the parametric equation is v sub 0 times cosine of theta. Now remember, theta is in degrees. So with theta being in degrees, that means that our graphing calculators, we're going to have to make adjustments to it when we do that, because our graphers are in radians. Okay? And all of that then is times t. The y part is going to be negative 16t squared. Okay, again with the shouting. Plus v sub 0 sine of theta times t, and then plus our initial height. Okay? That's just how strong I am.
I bet.
Just able to squeeze air right out of this ball. Okay? So, it's that time of year. Spring is in the air. It's actually spring now. Yesterday was the vernal equinox. Okay? Did you know that? That's what it's called? That's what it's called? First day of spring. Vernal equinox. Look it up. Okay? So that means it's what time, Paul?
Springtime.
Not March Madness time. That started already.
It's math time right now.
Well, but it's also baseball season. Did you know that baseball started last night too?
I did not.
Yeah, first games were played over in Tokyo last night.
Oh, really?
Yeah. A's and Mariners opened the season last night.
Sure, decided he was going to retire.
Well, I once he signed with I remember if he signed or got traded with the Mariners, and they had this game on the schedule, I knew he was going to retire after this one. He was just hanging on to play one more time in Japan, which is fine. Hey, good for him. Great career. Okay. All right. So we're going to talk about Lloyd Braun here. Okay, Roy, if you will. Okay. You know why I call him Roy?
No.
He was Rookie of the Year.
Oh.
Yeah. You know why I call him Lloyd Braun?
Why?
Seinfeld.
Never seen it.
Oh, Costanza's neighbor. Anyways, Ryan Braun hits a baseball which is 3 feet above the ground with an initial velocity of 150 feet per second at an initial angle of 18 degrees. Will the ball clear a wall 20 feet high 400 feet away? So, will he hit a dinger? Will he KR a ball? Huh? Right? Follow-up question, what is the maximum height of the ball? Okay? Alright? So, let's do this. Let's come up with a parametric equation for the ball. We're going to have to come up with two parametric equations. One for the ball, one for the wall. Okay? So, talk to me. What is my x equation for for the ball, or the x part for the ball. X part for the ball. Like that? Agree? You agree or not?
Yeah.
Yeah? You sure? Positive?
Yeah.
Okay, good, because I agree with it too. What's the y equation going to be? Just wait, Mark, we'll get to those in a minute. Yeah, because we got the tool, so let's make them first. What's the y equation? How's it start, Paul?
Negative 16t squared.
Love it. Good. Times t. And then plus 3, because we're 3 feet off the ground. Yes? T values. What do we want for our t values? What's the first one? 0. Okay. So t from 0 to what? 400? Does it take 400 seconds for a ball to get to the outfield? Two and a half, 3? All right. Let's go 3. Just to be on the safe side. If we went longer than that, it would just go, the path of the ball would just go underground. But we don't care about that because we're not even going to look over there. Right? Okay? All right? I love it. Now, that's the ball. Now we've got to come up with the wall. Horizontally, where is the wall? So that's going to be what in my function? So I'm going to have 400 here, correct? Because my wall is 400 feet away. How tall is my wall? 20 feet. So now I got to make a wall that's 20 feet high. How can I do that mathematically? There's more than one way to build this wall. It's got to be 20 feet high. But I can't just put 20 there, because if I just put 20, it's just going to put a dot 20 feet up in the air. So I got to bring a variable into it somehow. Say it.
T.
Okay, so if I go T there, right? Okay, so it's going to, if I plot a point, it's going to start out 400 feet, and it's going to be on the x-axis if I go start at 0, right? When would I have to end to make that wall be 20 feet tall? I have to end at 20. So if I do this, let me scroll down a little bit so the people in the back can see. So if I do this, my t value would have to go from 0 to 20 for that one. Could I do that one in purple? Could I have my y part be 20t and go from 0 to 1? Yeah? Okay. Because at 0 I plug in 0 and the height is 0. I plug in 1, the height is 20. And it would just connect it for me. Yeah. What about this one? Would that work? Yeah. Would that work? As long as it stops at 20 feet, it doesn't matter what my function is. It doesn't matter what my t's values are, as long as they make my function start at 0 and end at 20. Right? Okay? So we could have any of those. So what I want to do now is I want to graph that. So I am going to, you guys all have those written down? Yes? Okay? So then we can switch right to, I don't have to keep those up here, and I can go right to here. So we're going to start a graph, correct? New documentify yourself. Start a graph. We're going to have to switch to parametrics. Before I begin, is my calculator, which is the same as your calculator, is it in radians or is it in degrees?
Radians.
Why? How do you know that the calculator is in radians?
Rad.
It says rad up in the corner. Okay? Right? So because it's in radians, that means anytime I put a degree in, I've got to put the degree symbol. Where is the degree symbol? Where is the degree symbol? It's in the pi button, down here in the corner. Okay? It's in the pi button, and it's that one. I have to put that in, or I'm not going to get the right answer. And then that all gets times t. Where'd it go? Man. Ruh-roh, I don't see it. Gonna zoom out, change my window settings, probably gonna be faster than zooming out. Menu, window settings, okay. X's. What do I need to go out to? 450. 450-ish, okay. I'm gonna stick at -10 because I like to see my vertical axes. I'm gonna go by 50s on my scale just so there's not a lot of tick marks down there on the bottom. Y's. How high do you think that ball's gonna get?
45.
45?
Yep.
Okay. I'm going to go 50. I'm going to go by 10s. Did it hit? Did Ryan Braun hit a home run?
Yep.
He did?
No. I think he strained his oblique.
You don't even have a wall on there, Paul.
Yeah,
How do you know if he hit a home run or not?
I looked up there. How do you think that was funny?
What? He straightened his oblique?
Yeah.
Yeah. I was watching Paul type in. Sorry. Yeah. Straightened his oblique or struck out, really.
Yeah.
I mean, let's be honest. Yeah. If he's not straightening his oblique, he's striking out. Okay? So, home run, not a home run. Not a home run, right? Okay. So, he did not hit a home run. Let me capture this page for the notes for later. So in answer to the first question, no home run. The second question, the bonus question was, how high does the ball get? Okay. Well, in order to do that, I am going to have to solve this using algebra. Okay? So if I want to figure out how high the ball goes, I can do that one of two ways. Okay? One, I could do it graphically. Okay? So I can take this function. Let me go back up here with it. I can go right on top of this function. I can go back into graphing a function, and I can graph the y component of the parametric equation. Okay? It just so happens to be over here. Okay? And I can find the maximum of that graph. So the maximum of that graph says that at 1.45 seconds, we are 36.6 feet off the ground, okay, as my maximum height. That's one way of doing it. The other way of doing it is using algebra. Back in probably in Algebra 2, you learned that the maximum of an upside down parabola, which is what the path of my ball is, correct? Is an upside down parabola. You learned that that maximum happens where? maximum of a downwards opening parabola happen? Or the minimum of an upwards opening parabola? At the vertex. Okay? And so you learned that one way to find the vertex was to take the x part was equal to the opposite of b all over 2a. Well, in this particular case, the opposite of b here is negative of 150 times the sine of 18 degrees, because that's the b part of my quadratic. 2a is 2 times negative 16. So what I'm going to do now is I'm going to type that into a calculator page. I'm going to create a new page, a calculator page, and I'm going to type in that fraction. Negative 150 times the sine of 18 degrees divided by 2 times negative 16. Okay. Now that gives me a funkiness type 1. If I wanted to get the exact value of that, I would hit Control Enter. That gives me that. That's where that 1.44852 seconds comes in. And I'm going to store that. I'm going to store that value as t. Now, the reason that I stored that value as t is because now I can go back to my graph, and what I can do is I can trace my blue function. Control var. Okay. And what I can do in my trace, I can ask the calculator certain questions. Like right now I'm at 2.41 seconds. I can say, what about at 3 seconds? And I just hit 3, and it will go to where it is at 3 seconds. If I hit 1, it will go to where it is at 1 second. If I type t, it will go to where it is at t seconds. So at t seconds, which is the maximum, where I'm at my maximum, I'm 207 feet from where I made contact with the ball, and I'm 36.6 feet in the air. And both of those match up. Here is number 1, the first method. Here is the algebraic method of doing it. But both of those give me a maximum height of 36.6 feet in the air. Okay? Now, what I'd like you to do is I'd like you to figure out if Big Al hits a home run or not. Do you know who Big Al is?
Nope, but he will.
He will?
Hi, my name's Alfred Delia. At home they call me Big Al, and I hit dingers.
Big Al hits dingers. Okay? So you find out if Big Al hits a dinger or not. So we got the ball's function is going to be 75 cosine of 28 degrees times t. The y function is going to be negative 16 t squared plus 75 sine of 28 degrees times t plus 3.5. And we're going to go with a t value there again from 0 to 3. I think 3 makes it work. 3 does definitely make it work. And then we've got to do the wall. That's going to give me an x value. I want the wall to be 190 feet away. The y value, I need the wall to be 4 feet. So I'm going to go with t there again. And my t, oops, that should be an equals, not a dash. And my t values, I'm going to go from 0 to 4. Okay? All right, so go over to here. And then I want to get rid of this one. And then, oops. Hold on. Escape. Get me out of here. Get me out of here. Tab. Get rid of this one. There, it's gone. Now I want to go into here. Do my parametrics. This gets switched to 28. This gets switched to 75. That gets switched to 75. This gets switched to 28. This gets switched to 3.5. Oops, I forgot to hit enter. That's not going to help. 75, 28, 75, 28, 3.5, enter. Uh-oh. I don't think Big Al's hitting a dinger. Does Big Al hit a dinger?
Nope.
Nope. Big Al does not hit a dinger. Okay. Now, did anybody? I didn't uncover the second part of that one, but the second part of that one was what must the velocity be for him to actually hit a dinger? And that velocity is, I think it is 86 feet per second. Yep. And then he clears the fence. Okay. All right. Formative tomorrow.